Still one more chapter to go on equilibrium. And then we'll be done with it. Well, not really. But we'll pretend we'll be done with it. So this is now chapter 17. I believe it's officially called like additional aspects of equilibria or something, just other. And we're going to talk about a few more kind of special cases of types of equilibrium that we see in chemistry. And the first one is kind of a quantification of the Le Chatelier's principle. Remember with Le Chatelier's principle, we saw that, if we add a product, we shift to reactants and on all that fun stuff. Let's take a look at that now again. And we can do it in the context of acid-base since we just finished discussing that. So this is called the common ion effect. And the common ion effect comes into play when two processes produce the same ion in solution. And we'll see that one equilibrium will dominate the other. And for example, let's take a look at a combination of a solution has 0.1 molar HCl and 0.2 molar HF. We know the equilibrium constants of the dissociations of these, right? We know that we have HCl breaking into H plus and Cl minus, the Ka for which is very large. We also have the second equilibrium between hydrofluoric acid. And we know that this one is a weak acid, right? Ka is much larger than 1, or we'll just say larger than 1. And the Ka for this is 6.8 times 10 to the negative 4. Thereabouts. We don't need the unit there. So we can see very clearly that the HCl equilibrium is the dominant one. Its Ka is bigger. We looked at this when we were thinking about the acidity or basicity of salt solutions, right? So we have the HCl gonna dominate everything. So as a result, our solution, before we even worry about the HF, has 0.1 molar H plus and 0.1 molar Cl minus. And that's going to change what happens with HF. We will see that having HCl present in this solution will suppress the ionization of hydrofluoric acid. Because if we take a look at the ice table for HF dissociation, if we start with 0.2 molar, we're going to actually have some H plus in there already and no fluoride. We can calculate the amount of fluoride is actually probably more interesting right now. Although we could calculate the pH, we'll see that the pH will not change from what it would be with just the HCl, but we'll pretend. If we look at this, we'll still see that Q will be 0, because 0 times 0.1 is still 0. So we're still going to shift to make products. But the degree to which we're going to do that is much different than we would for not having this H plus in there. So let's subtract X from the reactant side, add it to the other. 0.200 minus X, 0.1 plus X, and then we have X. So we get X times 0.1 plus X over 0.2 minus X equals 6.8 times 10 to the negative 4. All right, so products over reactants, right? So if we go ahead and multiply this out, we get X times 0.1 over 0.2. Remember that with our approximation, the plus X and minus X go away. So X times a half equals 6.8 times 10 to the negative 4. So we need to multiply both sides by 2. So X is going to be, let's see, 6.8 times 2 is 14, so 1.4 times 10 to the negative 3 molar will be our H plus, or will be our F minus, right? So our F minus concentration would be 1.4 times 10 to the negative 3rd molar. H plus would be 0.1014. As we can see, not substantially different. If we were to do it without that difference of the, without having the X there. If we were to just take the pH of 0.1 molar or 0.2 molar HF, we would see it'd be quite different. We would have an X squared term, and we would need to do our square root, and we would get a much higher number for the fluoride. Let's just say we did that. So X squared over 0.2 minus X is 6.8 times 10 to the negative 4. Again, getting rid of that term. You multiply both sides by 0.2 now, and we're going to get, and then we have to square root it. So, calculator here. So, just for fun, we're going to take a look at this. So, e to the negative 4, square root this number, and we get X is 0.01166. So, comparing with the common ion, the fluoride was 0.0014 molar. Without just the pure HF solution, the F minus is 0.0117, we'll say, or whatever. We see it's 10 times as much without the common ion. So that's the common ion effect. It will suppress one of your equilibria from going to a farther extent. Again, essentially, we're adding a product or a reactant in the way that Le Chatelier's principle works. And so, without it, we see that we have much more fluoride than we do with the common ion. So, when we have solutions that have a common ion, we have to consider which equilibrium is going to overpower the other. Do that one first. In the case of HCl, it's not even an equilibrium. It's a one-to-one regular plain old reaction. But sometimes you may have to do ice tables for both or something. So you can always have fun with that. So this is going to come into kind of a great example of something very biologically relevant in the next section we're going to look at, which is buffers, which will be solutions that have common ions within them. And so we'll take a look at that in the next video.